Here we're going to look at an ARMA 2.1 model. In the sense it has an AR part of order 2 and an MA part of order 1. So the model can be expressed as xt minus v1, xt minus 1 minus v2, xt minus 2 equals at minus theta 1, at minus 1. And of course we could apply the usual backwards operator. So we would have xt minus v1 b times xt minus v2 b squared xt equals at minus theta 1 b times at. I could pull the xt out, have 1 minus v1 b minus v2 b squared equals at times 1 minus theta 1 b. This would give us the characteristic polynomials. Phi of s, which would be 1 minus v1s minus v2 s squared, and theta s, which is 1 minus theta 1 s. So the first one would be for the AR part, and the second is for the MA part. And keep in mind the roots of phi of s must lie outside the unit circle in the complex plane. And that would guarantee stationarity. And the roots of theta s must lie outside the unit circle. Which would guarantee invertibility. Now, invertibility is quite important because it is always easier to write an ARMA model in terms of an AR model rather than an MA model. Even though we could do it both ways, writing it in terms of an AR model makes things easier for us. They are typically easier to solve and easier to find the coefficients for. So how do we go about finding phi1, phi2, and theta 1 if we observe a series? So the very first step is to convert the series to an AR series. Reason being, as I said, it's easier to deal with the AR part rather than the MA part. So I'm going to divide both sides by 1 minus theta 1 b. So those two terms would go away, leaving us with just the left hand side. And I could rewrite this either in terms of the characteristic polynomial s, or just keep it in terms of the backwards operator. So I like to write it in terms of s. So 1 minus v1 s minus v2 s squared divided by 1 minus theta 1s equals AT. And since we have a constraint on theta 1, so that the absolute value lies or is less than 1 and not equal to 0, indicating invertibility. So we could write this as xd times 1 minus v1s minus v2s squared times 1 over 1 minus theta 1s equals a sub t. And as we've seen before, that would be the infinite sum of a geometric series. So we would have xd times 1 minus v1s minus v2s squared multiplied by 1 plus theta 1s plus theta 1s squared plus theta 1s cubed, and so on. Which I'm going to write it as 1 plus theta 1s plus theta 1 squared s squared plus theta 1 cubed s cubed, and so on. Now I'm going to FOIL things out. So I would have x sub t 1 plus theta 1s plus theta 1 squared s squared plus theta 1 cubed s cubed, and so on. So that is simply the first term 1 multiplied by the entire expression involving thetas. And I'm going to distribute the second term in with the expression. So I would get negative phi1s, negative phi1 theta 1 s squared, negative phi1 theta 1 squared s cubed, negative phi1 theta 1 cubed s raised 4, and so on. Distribute the next term, which would be negative phi2 s squared. I would have negative phi2 s squared, negative phi2 theta 1 s cubed, negative phi2 theta 1 squared s raised 4, negative phi2 theta 1 cubed s raised 5, and so on. That would simply give us, after simplification, 1 plus theta 1 minus phi1 times s, I'm combining like terms, plus theta 1 squared minus phi1 theta 1 minus phi2 times s squared plus theta 1 cubed minus phi1 theta 1 squared minus phi2 theta 1 times s cubed plus minus phi1 theta 1 cubed minus phi2 theta 1 squared. I'm going to just leave it as is, because I don't have to go for an infinite order. So now we can rewrite each of these coefficients that as the pi weights. We have pi 1, pi 2, pi 3, pi 4. So, of course, pi 0 is 1. Pi 1 would be theta 1 minus phi 1. Pi 2 would be theta 1 squared minus phi 1 theta 1 minus phi 2. I could pull out theta 1 from the first two terms. I would have theta 1 times theta 1 minus phi 1 minus phi 1 minus phi 2. But we know that theta 1 minus phi 1 is pi 1. So pi 1 minus phi 2. And moving on to the next term, pi 3, I would have theta 1 cubed minus phi 1 theta 1 squared minus phi 2 theta 1. I could pull out theta 1 squared from the first two terms, which would give me theta 1 minus phi 1 minus theta 1 phi 2. So I have a theta 1 in common between those two terms. So if I pull out theta 1, I have theta 1 times theta 1 minus phi 1 minus phi 2. But that term right there is simply pi 2. So I would end up getting pi 3 equals theta 1 times pi 2. So not so bad. Now, what I'm going to do is I'm going to go back to the original equation, and I'm just going to throw in one more term to see what happens. So I'm just going to add theta 1 raised 4, s raised 4, which would be the next term in the series. And when I distribute that theta 1 s raised 4 with that term, I would end up getting theta 1 raised 4 s raised 4 minus phi 1 theta 1 raised 4 s raised 5 minus theta 1 raised 4 phi 2 s raised 6, and so on. Now you may say, well, why is he doing this? I just want to go one more step in terms of s raised 4. So if I look at that and combine the like terms of s raised 4, that would give me the term for pi 4. So pi 4 would equal to theta 1 raised 4 minus phi 1 theta cubed minus phi 2 theta 1 squared. I have a theta 1 cubed in common in the first two terms. So if I pull that out, I would have theta 1 minus phi 1 minus phi 1 theta 1 squared. And if I pull theta 1 squared out, I'd have theta 1 times theta 1 minus phi 1 minus phi, I believe that should be a phi 2. Yes, it's phi 2. So it's right here. But if you notice that this is simply theta 1 squared pi 2. So because pi 2 is what we have up there. So you can see where this is going. So I have written pi 4 as theta 1 squared pi 2. But I could also write this as theta 1 times theta 1 pi 2. But I know that theta 1 pi 2 is pi 3. So I would end up getting theta 1 times pi 3. So if we use induction, it can be noted pi k would simply equal to theta 1 raised k minus 2 times pi 2, or we could write pi k to be equal to theta 1 times pi k minus 1, provided k is greater than or equal to 3. It cannot be equal to 2. It's not going to work. So just by having this, we could end up having all the pi coefficients using this recursion formula. And this is how we're going to estimate all the pi values. And keep in mind, as k approaches infinity, pi k would approach 0, which is why, even though we are writing an ARMA model in terms of an AR model with infinite order, we don't have to go for that infinite order. For some large p, typically the ARMA model would just reduce to a finite p. So we can rewrite our model xt minus pi 1 xt minus 1. So I'm going to go back and plug in those values. I have it as plus, so one plus pi 1 s plus pi 2 s squared plus pi 3 s cubed plus pi 4 s raised 4, and so on. And that would equal to a sub t. I could rewrite this as 1 minus phi 1 prime s minus phi 2 prime s squared minus phi 3 prime s cubed minus phi 4 prime s raised 4, and so on, and that would equal to a sub t. This would simply imply that phi k prime is simply negative pi k for all k greater than or equal to 1. Distribute the xt in, we'd end up having xt minus phi 1 prime xt s minus phi 2 prime st s squared minus phi 3 prime xt s cubed phi 4 prime xt s raised 4, and so forth would equal to at, but s and the backwards operator are one and the same, so x sub t minus phi 1 prime b times xt minus phi 2 prime b squared xt minus phi 3 prime b cubed xt minus phi 4 prime b raised 4 s4 equals at. Which would then become xt minus phi 1 prime xt minus 1 minus phi 2 prime xt minus 2 minus phi 3 prime xt minus 3 minus phi 4 prime xt minus 4 plus all the way up to infinity equals at. So what we have now is an AR infinite representation with the coefficients as phi 1 prime, phi 2 prime, phi 3 prime, phi 4 prime, and so forth. So we took an ARMA 2-1 model, and it had phi 1, phi 2, and theta 1 as the coefficients. We converted it to an AR infinite model with coefficients phi1 prime, phi2 prime, phi3 prime, and all the way up to infinity. Again, it is quite important to note that we don't have to go all the way up to infinity. We can stop at a particular order. Now, how do we determine the order? So we know that we have an ARMA P, Q, and P is 2 and Q is 1. So the maximum order to stop for estimation of model parameters is P plus Q, which in this case would simply be 2 plus 1, which gives us 3. So we can just stop at 3. So here we have an example. Suppose an ARMA 2-1 model has the following autocorrelations, and row 1 is 0.98, row 2 is 0.72, row 3 is 0.61, row 4 is 0.52, and we want to find or estimate the model parameters. We want to find phi2 and theta 1. So how would we go about doing this? So we know from Yule-Walker equations we have 3 unknown quantities, phi1, phi2, and theta 1. So all we need to find, or all we need to have is 3 equations. But before we get to the Yule-Walker part, we know the ARMA 2-1 can be converted to ARMA infinity, and here we're going to stop at order k equals p plus q, which would be 3. In other words, the equivalent model is xt minus phi1 prime xt minus 1 minus phi2 prime xt minus 2 minus phi3 prime xt minus 3 equals a sub t. This is an intermediate step. So we are going to make use of the AR3 representation and the autocorrelations to find the actual ARMA 2-1 model. So now we could go to the Yule-Walker equations. So we have row 1, row 2, row 3. I'm extending the standard 2 by 2 case to a 3 by 3 case, And the easier way to form the matrix is if you write it as 1, 2, 3 here, 1, 2, 3 there. 1 minus 1 would be 0, and rho sub 0 is simply 1. 1 minus 2 is negative 1, and autocorrelations are symmetric, so I would simply have row 1. 1 minus 3 is negative 2, again using symmetric property, we would have row 2. 2 minus 1 is 1, so we have row 1. 3 minus 1 is 2, we have row 2. 2 minus 2 is 0, and row 0 is 1. 2 minus 3 is negative 1. Using symmetric property, we have row 1. 3 minus 2, 1, so we have row 1. 3 minus 3 is 0, row 0 is 1. And that would be the Yule-Walker equations for the model that we simply have from the ARMA 2-1 model. So we could go on and plug in these values, 0.98, 0.72 and 0.61. So we would use the calculator to find the solution to these matrices, or to this system, not matrices. So I'm going to call that as A and that as B, and that would be the phi vector. So the solution, or phi prime, would simply be phi 1 prime, phi 2 prime, phi 3 prime. That would equal to B inverse A. A is a 3x1 matrix, and we have 0.98, 0.72, 0.61, and the B matrix is 3x3, we have 1.98, 0.72, 0.98, 1.98, 0.72, 0.98, and 1. And I'm going to find B inverse A, and those are the values that I end up getting. So phi prime is 0.2155, 1.593, negative 1.106. So what we know here is phi 1 prime is 0.2155, phi 2 prime is 1.593, phi 3 prime is negative 1.106. And keep in mind, we are trying to find the model parameters for the original model, which is ARMA 2-1. So we know that pi k is negative pk prime for k greater than or equal to 2. So pi 2 would equal to negative 1.593. Pi 3 would equal to negative 1.106, and it would become positive. So let's start with pi 3. Pi 3, we can't write the same recursion for k equals 1 because the recursion holds true for k greater than or equal to 2. We know pi 3 is simply theta 1 times pi 2. So, which would imply theta 1 is pi 3 divided by pi 2. So 1.106 divided by negative 1.593. We have negative 0.6943. We could go back one more step. We know pi 2 is theta 1 times pi 1. Which is right over, oh, sorry, we can't do that. It's theta 1 pi 1 minus phi 2, because the recursion holds only for k greater than or equal to 3 when it comes to pi 3, or the pi's. So we know pi 2 is negative 1.593. We just found theta 1, which is negative 0.6943. We know pi 1, which is negative 0.2155 minus phi 2. So negative 1.593 would equal to 0.6943 times 0.2155. 0.1496 equals or minus phi 2. Move things to the other side. We have minus 1.593 minus 0.1496. So negative 1.743 would equal negative phi 2, which would imply phi 2 is 1.743. Now we have the value of phi 1, excuse me, theta 1 and phi 2. We go back to the original equation for pi 1. Pi 1 is right here, which is theta 1 minus phi 1. So all we have to do is find phi 1. Pi 1 is negative 0.2155. Theta 1 is the value we just found, negative 0.6943 minus phi 1. Simplify, we would have 0.6943 minus 0.2155. .4788 equals minus phi 1, which would imply phi 1 is negative 0.4788. So now we have to go back to our original model. xt times I simply plug in the values of phi1, so I have xt minus 0.4788 multiplied by xt minus 1 phi2 is 1.743, theta 1 is minus 0.6943. So we end up getting xt plus 0.4788, xt minus 1 minus 1.743, xt minus 2 equals AT plus 0.6943 AT minus 1. And we have successfully found the ARMA 2-1 model. Keep in mind there are better methods to find the coefficients. This is the simplest one we have. Oftentimes in practice, we use computational methods to find the solution. Here is another example. We want to find the psi weights of the ARMA 2-2 model given by that, and we know the coefficients phi1, phi2. Phi1 is 0.5, phi2 is 0.25, theta 1 is 0.6, theta 2 is 0.4. So we want to find the psi weights. Psi weights are obtained by rewriting ARMA in terms of MA infinity, and pi weights are obtained by rewriting ARMA in terms of AR infinity. So how do we go about it? So I want to rewrite it in terms of MA. So I have AT times 1 plus 0.6s minus 0.4s squared divided by 1 minus 0.5s minus 0.25s squared. This is where algebra comes into play. What we are going to do is something you probably didn't like in algebra: fun long division. So I'm going to put 1 there, so I get 1 minus 0.5s. Let me limit the question. I said psi weights for the ARMA 2-2 model, which would mean we would have infinitely many. We will just say the first 5 psi weights. Psi 0, psi 1, psi 2, psi 3, and psi 4. Minus 0.25s squared. We subtract. Those two would go away. 1.1s minus 0.15 s squared. Now we multiply by 1.1s. We get 1.1s minus 0.55 s squared minus 2.275, I believe, or 2.75. No, 0.275 is cubed. Subtract, and we would have 0.4 s squared plus 0.275 s cubed, and 0.4 s squared, 0.4 s squared minus 0.2 s cubed plus 0.1 s raised 4. It's minus, actually. Subtract. Those two would go away, and we would have 0.475 s cubed plus 0.1 s raised 4. Plus 0.475 s cubed, I have 0.475 s cubed negative 0.2375 s raised 4 minus 0.11875 s raised 5. Subtract 0.3375 s raised 4 plus 0.1188 s raised 5. And it is going to keep on going. And you can actually see as to why this process could get easily complicated if we try to do this manually, which is why we have the need for computational methods, and there are plenty of computational methods to achieve the goal. And it's going to keep on going, but we just want to find the first 4 psi weights, and we actually obtain the psi weights, the first 4 of them, or first 5, 1, 2, 3, 4, 5. So psi 0 is 1, psi 1 is 1.1, psi 2 0.4, psi 3, 0.475, psi 4, it's 0.3375. So those are the psi weights, and the equivalent MA infinity representation is xt equal to AT plus psi 1 AT minus 1, psi 2 AT minus 2, psi 3 AT minus 3, psi 4 AT minus 4, and so on. So we could just do the reverse of what we did. In other words, we could take the left-hand side expression, 1 minus 0.5s minus 0.25s squared, divided by 1 plus 0.6s minus 0.4s squared, and we can end up finding the AR infinity representation using a similar long division process.